Welcome to Paris 123, and today we're talking about the different ways that a boundary layer can transition from laminar to turbulent. So there are a few different ways, and in our other podcasts, we've covered a few of them here and there, but this is really the first podcast where we're going to be going through the major ways. So to do that, we're going to look at a paper called Transition Models for Turbomachinery Boundary Layer Flows, a review. This is open access again, so you can find it in the link in the description. And like always, if you want to, actually, this paper is going to be quite long. It's 45 pages. We're not going to go through all of it. We're going to go through the major parts. A lot of the parts that we're not going to go through are mainly the mathematics behind RANs and URANs turbulence modeling. If you want me to go through that, let me know in the comments below. And in the next few podcasts, I'll go through that if you like it. If not, we'll go on to something else. Just this podcast, we'll go through the general theory of these transition mechanisms. So let's start. So I should actually qualify first. Transition is where you have a boundary layer, which is laminar, and then it goes to turbulence. So that's a transition regime. Once it's ended, then we say that the boundary layer is fully turbulent. If there is no turbulence at all, then it's fully laminar. So with the objective of modeling Reynolds average Navier-Stokes, or RANs or URANs, descriptions of a flow, generally four types of transitions from laminar states to turbulent states in turbomachinery boundary layer flows are distinguished. And this is generally similar to the flat plate situation as well. So a turbomachinery environment is very similar to just general aerodynamics. There are some peculiarities which we'll go through, but most of this is very applicable to all flows. So these four general types of transition from laminar to turbulence are natural transition in attached boundary layer states, bypass transition in attached boundary layer states under a statistically steady mean flow, separation induced in transition in the free shear layer formed by separation of a boundary layer under a statistically steady mean flow. And the fourth way is wake-induced transition due to periodically unsteady impacts of wakes on boundary layers in attached or separated states. So let me just cover this briefly again. Yeah, first, which is the natural transition way, which is when you have a very subtle like perturbation, which then grows. The second way is bypass transition, and this is where you have a very big perturbation, and that just like breaks down very quickly. You then have separation-induced transition, which is also known as like laminar separation bubbles that I've talked about a lot in other podcasts. And finally, when you have a wake, which is impinging on another thing downstream, that wake is going to obviously be a lot of unsteady motion, and that can trigger transition as well. So these are the four major ways. And it should be noted that between the natural state and bypass transition, so these two first ones that I talked about, there are a few different states along the way. So this is actually 5 substates that you can have between these. I'm not going to go through those ones because it's a very in-depth study, which I'll probably go through at a later date in another podcast. But in this podcast, we're going to go through these major 4 ways, and then in later podcasts, probably break them down into even more detail. So first of all, let's talk about natural transition. So under a statistically steady mean flow of low turbulence level, so this means that if you get the entire flow over time, it just averages out to being very like steady. There's no changes in the mean velocity. There is obviously a turbulence level, which every flow does have, but in this case, it's a low turbulence level. So how much is a low turbulence level? Well, generally speaking, this is below about 1%. So if you have around 0.5, 0.1%, that's classified as like a low turbulence level, and that's going to facilitate natural transition. Now, this is not necessarily always going to happen, as because in other podcasts that I've mentioned, transition is not only affected by Reynolds number or surface roughness or turbulence level, it's affected by all 3 of these things. So having a high turbulence level, for example, 5%, if you have a really smooth surface and a very short surface, well, you're not going to get transition to turbulence on that surface. On the other hand, if you have a turbulence level of 0.1% or 0.01%, and you have a very rough surface and a very long surface, then you're definitely going to get a transition to turbulence, and it could be a much more chaotic motion than just a natural transition. So it really depends on other factors as well. But let's say that we have like a fairly smooth surface, a fairly low Reynolds number, and we have a low turbulence intensity level. That's going to result in natural transition. And this transition is an attached boundary layer that is initiated by a 2D viscosity dependent Tollmien Schliting instability wave, followed by a 3D instability, leading to formations of spanwise periodic hairpin vortices, which further break down downstream, causing a breakdown of the laminar layer with general turbulent spots. So what does all this mean? We haven't even covered the last little bit of the turbulence transition yet. We just covered the formation of these initial Tollmien Schliting waves they break down three-dimensionally to hairpin vortices, which then generate turbulent spots. So let me discuss what all this means. So let's say we have, for those of you listening to this on Spotify, you can watch the video on Spotify as well, and or on YouTube. On YouTube, you also get a few of our other little goodies, like some cool CFD videos, but either way, you can watch the video there. So let's say we have just a regular surface, and the flow is coming onto it as a u-infinity velocity. As we come along, we're going to have these little wiggly waves forming, and they're going to form along the entire surface here. And as we go further downstream, these waves are going to, and if it does transition to turbulence, they're going to start to break down two-dimensionally, which then transitions to three-dimensional breakdown. And this is something that's very interesting with turbulence, that a two-dimensional phenomenon can break down three-dimensionally. That's like a cornerstone of boundary layer transition phenomena. And for a long time, it wasn't really believed, but it has been proven like a few decades ago, I guess, that three-dimensional effects do occur from two-dimensional effects, and then we don't need to have a three-dimensional disturbance to get three-dimensional turbulence. Pretty much everything that's two-dimensional will break down three-dimensionally, unless like the viscosity really tears it apart and really suppresses it. But let's assume that the Reynolds number is high enough that the viscosity will not suppress this perturbation, and this perturbation will start to develop. So we get this two-dimensional Tollmien Schliting wave first. It breaks down three-dimensionally, and we start to get like these sort of hairpin vortices, they call them, which is where a vortex sort of wraps around in like a horseshoe shape. And then they break down three-dimensionally into turbulent spots. So you have all these little turbulent spots everywhere that form. So a spot here, a spot there, a spot there. Then they break down even further. And then these lines indicate where all this turbulence is occurring. And then finally they meet at some point, and now the entire boundary layer is turbulent. That's how this mechanism works. This Tollmien Schliting mechanism works. I jumped ahead a little bit there. I talked about the turbulent spots and then the final transition. So these spots finally merge, resulting into the formation of a turbulent boundary layer. That's what I mentioned at the last bit here. But that's this general mechanism. And this type of transition is called natural transition. It is a rather slow process and under a very low mean flow turbulence intensity level, as in external aerodynamics. And it is very sensitive to all sorts of perturbations. So this is actually something we should talk about. How can we develop perturbations? How can we introduce perturbations to a system? Well, among other things which are very obvious, for example, if you just have an object which has like a weight coming off of it, or a rough surface, or just any change, like a little bit of dust or whatever. Also, other things like if you have a table and it moves, or if you have sound and it's propagating into the boundary layer, these can all trigger turbulence. They trigger perturbations, and these perturbations can break down into turbulence, even sound, which we'll cover a little bit more later as well. So this makes the prediction of transition in external aerodynamics very delicate, which means that when we go to RANS and URANS situations, and even DES, where we are using turbulence modeling, this is the major problem here, where if we have a low turbulence intensity level, trying to predict how the boundary layer is going to transition becomes very difficult because it is so delicate. And that's why in other podcasts, I go on and on about different turbulence models and their shortcomings, and when you should use ones in certain situations, when you shouldn't use them, because of this situation here, where if you have very different boundary layer setups and very different flows, the boundary layer could transition very differently. And RANS and URANS, some of these models, generally speaking, are not capable of like just modeling everything. Like if you have a certain situation, you need to use a certain turbulence model. As I've mentioned in other podcasts, my favorite is K-Omega, I should mention, because that is the most robust I've come across. Like that's the one that you can really just set it and forget it. And it does a pretty good job with everything. But even then, it does fall short sometimes, but that's usually due to mesh grid-like resolutions. But still, you should always pay attention to what you're using. So in turbo machinery flows, though, the mean flow turbulence levels are never very low, and so turbulent fluctuations perturbing the pre-transitional boundary layer amplify and control the Tollmien Schliting wave growth. This makes the transition process much less sensitive to other kinds of perturbations and much more amenable to simple descriptions by correlations or characteristic sensor numbers. So what does this mean? If we have an external flow like a table, the flow over it is usually quite well behaved, like there's a very low turbulence intensity level. So what this means is that trying to predict this transition with RANS or URANS or DES is quite difficult. If you go into turbomachinery, the turbulence level is usually very high, like 5% maybe. So that means that going down the path of natural transition is usually not that common. And so even if it is happening, it's still very easy to predict compared to regular external flows. So that's what I mean here. You can then use the empirical data that we get to develop the turbulence models, like the K omega or K epsilon or SST or whatever, and they work quite well because the flow in these environments are very harsh and they are blunt, really. Like they're very easy to predict because they are not delicate flows. So that's the first type of transition, natural transitioning. What about bypass transitioning? I've talked about this one in other podcasts as well, but let's cover it here in more depth. So under a sufficiently high level of mean flow turbulence, generally above 0.5% or 1%, again, depends on the Reynolds number and the surface roughness. But if we have turbulence levels above this, streamwise elongated disturbances are induced in the near wall zone or of an attached laminar boundary layer, termed streaks or Klebanoff distortions. And this Klebanoff distortion is somewhat similar to natural transition. It looks very similar. And what this is actually, I'll just describe it a little bit more and I'll just draw it a little bit later. So these are zones of forward and backwards jet-like perturbations, alternating in span-wise directions with almost perfect periodicity, with a wavelength in the order of the boundary layer thickness. The streaks are caused by deep penetrations of low-frequency disturbances, while high-frequency disturbances are strongly damped by the laminar shear layer. This damping is called shear sheltering. The laminar boundary layer, distorted by the streaks, is susceptible to instabilities. A remarkable feature is that the streak patterns are of a large wavelength, but that the instability patterns are of a short wavelength. This means that the instability pattern can only be excited by high-frequency perturbations. Although these are damped by the boundary layer shear, the Klebanoff distortions grow downstream both in length and amplitude and finally cause breakdowns with the formations of turbulent spots. The transition is then called bypass, which means that the instability mechanism of the Tollmien Schliting waves is bypassed. Flow breakdown is then much faster. So let me discuss what this is. And as I mentioned, it looks very similar to the natural transition, but it is faster and more harsh. So again, if we have a flow, a flow over the table, we have a U infinity free stream velocity. We have these Klebanoff disturbances, which then break down into turbulent spots again, and they then merge at some point where you now have complete turbulence. And upstream, these Klebanoff disturbances, as they mentioned, they are like these jets. So you have one jet, which is pushing the flow downstream. You have the next jet, which is right next to it, pushing the flow upstream. And the next next jet next to it, pushing it downstream, and so on and so forth, periodically. And the length between each one of these is approximately the same height as the boundary layer. So it's of the same order of magnitude. And they are not only two-dimensionally spaced, but also three-dimensionally spaced as well. So if you look from the other direction, so looking down into it, you'll see that going, like let's say we have the table here, and the flow is going over it. We then have these jets as well forming. So one here, one there, one here, and they just form periodically. And that breaks down three-dimensionally into these turbulent spots downstream. So when we get to the turbulent spots, the turbulence looks very similar to the natural transition approach. But if we look before that in this Klebanoff situation, the mechanism that's causing these turbulent spots are very different to the Tollmien Schliting method. Like the Tollmien Schliting waves are not there. So that's the difference there. Even though the end result looks very similar, the cause of that end result is different. So for modeling with RANS and URANS descriptions of a flow, the details of instabilities are not relevant here. And this is because we have such a high turbulence intensity level, and these Klebanoff modes are very easy to model, that RANS and URANS turbulence modeling becomes much more accurate, and that way you don't really need to worry about all the little details of the flow because they're not important. The important bits are the macroscopic or like the mesoscopic level, which are these little jets that are forming. So that's the second type of transition. Let's talk about the third type now. So the third type is separation-induced transition. And if you've listened to our other podcasts, you'll know that we've talked about LSBs a lot. Laminar separation bubble is, let me draw this out here, is where you have say just a flow over a table, and then you have the flow coming along it. It's laminar to begin with. Then at some point it will detach. and then it will reattach at another point downstream and continue along its way. And at the point of reattachment, it's already turbulent, usually. They mentioned in this paper that it's not always the case, but every study I've ever read about LSBs, this is the case. And they've determined that the transition occurs a little bit further upstream than the reattachment point. And in this LSB, the flow does recirculate. So that's the separation-induced transition. Let's discuss this method here, or this mechanism here. In a boundary layer with laminar separation and a low or moderate mean flow turbulence, transition is initiated by an implicit Kelvin-Helmholtz instability of the laminar free shear layer with generation of span-wise vortices. So what is this Kelvin-Helmholtz instability? Well, you probably have seen it without even realizing that you've seen it. If you look up at the sky when a plane is going overhead and they have those contrails, the Kelvin-Helmholtz instability does form there, as well as the Coulomb stability when the flow breaks down. But anyway, I'm getting ahead of myself. Let's say we have two flows. We have one flow going this way at 5 meters per second. We have another flow just above it at 10 meters per second. I should probably draw this arrow bigger. So it's moving faster. The shear layer between them, so this interface between them, is where this Kelvin-Helmholtz stability occurs. And what you have is one flow is moving faster than the other, so it's going to be producing these like roll-up parts on this shear layer. What's happening is the flow between these two are mixing, and they're getting ripped apart between these two jets, or between, technically speaking, one's a jet, one's a wake, but I'll get into that in a second. They're getting ripped between these two different velocities of flow. And that means that some fluid is like being ripped off of the slow fluid and rolling up. That's the Kelvin-Helmholtz stability. A minute ago, I mentioned jets and wakes. I should probably talk about the definition between the two. So a jet is when the fluid is moving faster than the fluid around it. A wake is when it's moving slower. And this will actually change how this roll-up of these vortices between these two different moving like speeds of flows rolls up. So you might get, instead of rolling up this way, it might go down, or it might roll backwards, or whatever. It depends on the interface there and the velocity differences. So the boundary layer, the turbulence is really introduced by this mechanism, this Kelvin-Helmholtz instability. The roll-up of these vortices become unstable by span-wise perturbations and cause breakdowns as they convect downstream. So in other words, these vortices, like any vortices really, they will break down over time downstream, and that introduces all this like unbridled turbulence, and that can result in transition if the Reynolds number is high enough. This is a slow process that is sensitive to all sorts of disturbances under very low mean flow turbulence. As with natural transition, mean flow turbulence accelerates and controls the growth of Kelvin-Helmholtz vortices and makes the process less sensitive to other disturbances. So generally, the free shear layer, once sufficiently turbulent, reattaches, forming a separation bubble, as I mentioned. For this result, transition into turbulence does not have to be complete at the reattachment point. Now, I disagree with this. As I said, pretty much every experimental and most CFD that I guess every CFD study that I've seen, they've all proven this, that it's already transitioned to turbulence by the time it has reattached. For quite a while there was a debate about whether it does or doesn't. And some people were saying that as soon as it touches it only touches down and reattaches when it's transitioned. So as soon as it transitions to turbulence, that's when it reattaches. And other people were saying, well, it can transition later downstream once it's already reattached. But it seems like, from my knowledge, that it always has transitioned before it's reattached. So it's in that separated zone that the transition occurs. But anyway, let's move on. Under a low or moderate mean flow turbulence level, natural transition upstream of the separation point by Tollmien Schliting waves can coexist with the Kelvin-Helmholtz vortices in the separated layer. So in other words, in the boundary layer that's already attached, you can have this Tollmien Schliting wave occurring, which is this natural transition. Then in the part where it has detached, it can have this Kelvin-Helmholtz instability forming. So you have these two instabilities forming effectively that are trying to drive this boundary layer to turbulence. So it's like a double transition almost. And what's more, if you have a high turbulence level, they say similarly under a higher mean flow turbulence level, bypass transition with the formation of streaks in the pre-transitional attached boundary layer can coexist with the Kelvin-Helmholtz vortices. So in other words, this Kelvin-Helmholtz instability, this separated induced in transition, can coexist with other forms of boundary layer transition, not only the Tollmien Schliting waves, but also the bypass transition as well. The breakdown of the vortex rolls is then accelerated by the perturbations due to the Klebanoff distortion, so they work together. For sufficiently strong mean turbulence flows, the Kelvin-Helmholtz instability may even be bypassed by the breakdown due to streaks. So in other words, if the flow is already transitioned by the time you want to get to like this LSB, then you're not going to get this LSB forming, the laminar separation, but with this separated induced flow. So a bypass mechanism is possible similarly in an attached boundary layer. So that's the third way, using this where the flow detaches and you have this roll up of these vortices because of these two different velocities of flows, and there's a shear layer between them, and that then introduces a lot of this perturbation, which then transitions to turbulence. The fourth way is wake-induced transition, and it's very much what it sounds like. So in turbomachinery flows and other flows that have wakes, the transition is strongly determined by impinging wakes generated by preceding blade rows. With low or moderate kinematic perturbations by the impinging wakes, the induction of Klebanoff distortions is similar as with mean steady flows. So in other words, you have the flow from one blade going over it, you have a wake that's hitting the blade downstream, and that's just causing all this turbulence, which then triggers the boundary layer transition to turbulence. That's a very easy mechanism to understand. There's a lot of other information here that they have, but it's not really that important for the general details of this mechanism. It's more just very specific to turbomachinery, which we're not going to cover because this is just general turbulence here. But we'll talk about intermittency now. So we talked about four different general ways of a boundary layer to transition. There are many sub-ways, like little details that do change, but we're now going to talk about intermittency. So the concept of intermittency was introduced by Narashima. It's commonly used in analysis and descriptions of transitional boundary layer flows. The intermittency is the fraction of time that the boundary of the flow is turbulent in a position in the boundary layer during the breakdown phase. So in other words, it is 0 in a laminar flow and 1 in fully turbulent flows. The style of transition is defined as the foremost position in the boundary layer where turbulent features become visible, which means that the intermittency begins to deviate from 0. The end of the transition is the foremost position where the full flow may be considered as turbulence, which means that the intermittency approaches 1. So the concepts of start and end of transition are only loosely defined. Let me cover a bit better what this intermittency means in a bit more detail. So if we have the flow going over a table again, let's say, and it's moving at 1 meter per second or whatever, it doesn't really matter. And we have at this point here, we start to get some sort of turbulence forming. Like it's not, the boundary hasn't transitioned yet, but we're starting to get a little bit of turbulence. Here, we say that the intermittency, which is often denoted by gamma, is now greater than 0%. So, or 0, I should say as well. It depends on how you want to express it. Then we go downstream a little bit further. And at this point, we can now say at 50% of the time at this point, the boundary layer we are considering is turbulent. At 50% of the time, it is laminar. So here we say the intermittency gamma equals 0.5 or 50% or whatever, however you want to describe it. Then we go down a little bit further and we say here, at this point, the boundary layer is turbulent 99% of the time. So the intermittency gamma is 0.99. If it's 1, it means that it's completely turbulent all the time, which I'm not sure you can actually get 1. Like you can get like, I guess 0.9999. Like 1 is the limit, but that's the general theory of it. That's what this all means here. So the concepts of the start and end of transition are only loosely defined because it really depends on how well you can pick up these disturbances and how you classify them. In the very first phase of transition research, laminar and turbulent states were detected by the values of the wall shear stress. This implies that the distinction can be made between a laminar and a turbulent value, which for instance is possible for 0 pressure gradient mean steady flows over a flat plate. What does this mean? What they're saying here is in the early days when they were researching turbulence, they were looking at the flow over a wall or whatever surface, and they're looking at what the shear stress was at the surface. So in other words, how the velocity changed with changing height. So if we go up a little bit, so a value of y off of the wall, what was the value of the velocity here? and they looked at how much that changed. And they thought that, well, if it changes a lot, we can then say, okay, the boundary layer is turbulent here. If it doesn't change very much, it's laminar. And this is a very intuitive way of looking at it, because we know that boundary layers, the velocity profiles are very different depending on whether it's laminar or turbulent. In a laminar flow, it is very gentle, the increase to like the velocity as we go up away from the wall. For a turbulent flow, the velocity increases very dramatically, even a little bit of a distance away from the wall. So that's a general idea as to why we could use shear stresses to determine whether, or the wall shear stresses I should mention, to determine whether a flow is laminar or turbulent, but it's not the be-all and end-all. It's not completely infallible. So later on, they said, this type of detection only allows the definition of an intermittency at the wall and not in the interior of the boundary layer. So in other words, it only looks at the wall and not what's happening in the rest of the boundary layer. And that's important. What's happening in the wall is not the entire thing. It's not the entire picture. So later on, the turbulent state during transition was detected by analysis of spectral properties or distribution properties of velocity component fluctuations. So in other words, it looked at how the velocity was changing throughout the entire boundary layer and how violently it was changing effectively. And if it changes a lot, then very quickly, then we know that, okay, it's probably turbulent. That's another way of looking at it. Turbulent scales are much smaller in the interior of the turbulent spot inside a transitional boundary layer than in the outer flow. So in other words, where you're looking at in the boundary layer, and even in the free stream flow, the turbulence has a different wavelength effectively and a different frequency as well. So in the turbulent spots, they are much smaller, which means that the turbulence is effectively taking on a different look compared to the rest of the flow. So that's something to be aware of as well. Then they also go through in this paper a bunch of different ways of looking at turbulence, for example, wavelets and using Hall heat fluxes. I'm not going to go through those because at the end of the day, they are all better, but they're not infallible again, and this is still an ongoing process. But finally, intermittency evolves in the wall normal direction very sharply from 0 at the wall to a maximum in the wall vicinity, which typically forms a plateau of up to 20% of the boundary layer thickness. Far from the wall, it evolves gradually until a 0 value in the free streams. In other words, this is another way that we can sort of classify if a flow is laminar or not. If we have the intermittency increasing very rapidly away from the wall, like you go right at the wall and you go up a little bit and the intermittency has jumped up so much, we can kind of determine, okay, the flow is now turbulent. And if you go up like past 20% of the boundary layer thickness and then the intermittency starts to gradually increase a little bit, then that's also a good indication that the boundary layer is turbulent still, because the intermittency is still so high and it's not changing very much. That's another way of determining if the flow has transitioned to turbulence or not. So with that, I'm going to leave this podcast here, and because this is a nice place to finish, I think. The rest of this paper is really just talking about different equations and how to model turbulence in RANs and URANs. If you want me to go through that, let me know, and I will. Otherwise, it's mathematically intense. I don't mind though. If you don't mind, let me know in the comments below. If not, then we'll finish this podcast here, and I'll just sum up the different transition methods. The first one was the natural transition, which is using Tollmien Schliting waves. That's where you have very small disturbances which grow little by little, and then they finally break down two-dimensionally, then three-dimensionally, and then we get turbulent spots, which are these little concentrated parts of turbulence, like these little eyes of turbulence, and then they break down even more, and then there's turbulence everywhere. The second way is bypass transition, which is where we have a very high, like a very strong perturbation, and then that just like introduces all this turbulence into the flow. And what happens is we get these Klebanoff modes, which are these different jets forming everywhere in different directions, and that just really fuels this turbulence, and that's how the boundary layer breaks down. The third way is separation-induced transition, which is where we have these LSBs forming. That's where the flow going over a surface, it detaches. It's still laminar at this point. It detaches, and then the transition occurs while it's detached, and then it attaches and reattaches, and it's turbulent now, and with this recirculation zone in there. These researchers said that when the flow is attached, it's not necessarily fully turbulent. However, as I mentioned, I haven't seen any data indicating otherwise. And finally, wake-induced transition is where we have the wake of another object impinging on this object that we're interested in, and that really fuels this turbulent process. So these are the 4 ways, general ways. And in other podcasts, we're probably going to go through them in more detail, each one. And if you want to learn more about theory like this and or CFD, check out our course in the link description. And if you want to make your experiments 2 to 4% more accurate, check out the Atmosphere Hawk. The reason why is this is an instrument that we make, which actually measures the density of air. The reason why this is important is because the density of air changes every day by 2 to 4%, or even more. So if you come in the morning and you do your experiments and you come back after lunch, the density of air is going to be different, and your experiments are going to, if you operate under the same density of air assumption, then your experiments are going to have a 2 to 4% error in them. If you then come back tomorrow, the next day, next week, the next month, whatever, your experiments are going to have even greater errors in there because the density has changed even more. It's not unusual for the density of air to change 10 or 15% between seasons, for example. So then if you get your data and you try to process it, all these changes, which are only 2 or 3%, they're going to be hiding in the error of the density changes. What's more, if you use this data to try to validate your CFD is not going to be validated properly because your CFD density of air is different to your experimental density of air, and the density of air in your experiments is changing. So your validation data is all over the place, and you don't know that. So Atmosphere Hawk is an instrument we make which gets rid of that error for you. Link in the description for that, and I'll see you next podcast. Peace out, amigos.